Hey everyone, welcome back to the channel. In this masterclass we are doing a complete, from the ground up deep dive into design a distributed rate limiter. By the end of this video you'll understand it well enough to use it confidently in production and explain it clearly in an interview. If that sounds good, make sure you are subscribed and let's get started. Rate limiting is one of those topics that looks simple on the surface but hides enormous depth underneath. We are going to build the mental model from scratch, starting with the core problem it was invented to solve, the threat categories it defends against, and where it actually lives in a real production architecture. An API is fundamentally a shared resource. The database connection pool, the thread pool, the CPU, all of these are finite, and all clients compete for them simultaneously. A single client in a bad retry loop, like the payment service incident, does not need malicious intent to cause a full outage. It just needs to arrive faster than the system can drain the queue. Rate limiting is the contract that prevents any one caller from consuming more than their fair share. Quick pause. If this is useful so far, drop a like, subscribe for a new masterclass every week, and share it with a teammate who would find it useful. Now, back to it. Rate limiting defends against 4 distinct categories of harm. Accidental overload, like the 3 AM incident, is the most common and the most preventable. Scraping and enumeration attacks quietly drain capacity and exfiltrate data. Credential stuffing turns your login endpoint into an attacker's brute force engine. And volumetric denial of service, even without a botnet, can be achieved by a single misconfigured integration partner sending traffic at the wrong scale. One mechanism, 4 threat surfaces neutralized. A common mistake is treating rate limiting purely as a security concern. It is equally a fairness and economics mechanism. In a multi-tenant SaaS product, rate limiting is how you guarantee that a free-tier user's traffic spike does not degrade the experience for a paying enterprise customer. It is also how metered APIs enforce pricing. A customer on the 10,000 requests per day plan simply cannot consume 100,000. And critically, it is your first line of graceful degradation, shed load at the edge before it reaches the database. In a standard production architecture, the rate limiter lives at the API gateway layer as close to the network edge as possible. This placement is deliberate. By rejecting excess requests at the gateway with a 429 response, we prevent the load from ever reaching the auth service, the business logic layer, or the database. The further downstream a request gets before being rejected, the more resources it has already consumed. Enforce early, enforce at the edge. Here is the trap that most teams fall into. They add a rate limiter to their service, deploy it, and assume the problem is solved. But the moment that service scales horizontally to 10 pods, the rate limiter breaks. Each pod maintains its own independent counter, so a limit of 1000 requests per minute becomes 10,000 requests per minute cluster-wide. The only correct solution is a shared, atomic counter that every instance reads from and writes to, and that is exactly what Redis gives us. That is the distributed part of distributed rate limiting. There are 5 rate limiting algorithms you need to know, and you need to know them precisely, not vaguely. Each one has distinct behavior at the edges, distinct memory characteristics, and distinct failure modes. We will go through each one in turn, and by the end you will be able to choose the right algorithm for a given constraint, not just name them. Fixed window counter is the simplest approach. You divide wall clock time into discrete buckets, say, 1 bucket per minute, and keep a counter per caller inside that bucket. When the counter hits the limit you reject, when the clock ticks into the next bucket you reset. The fatal flaw is the boundary burst. A caller can send the full quota in the last half second of one window and the full quota again in the first half second of the next, doubling their effective rate right at the seam. The Redis implementation of fixed window is a single INCR call on a key scoped to the caller identity and the current window index. On the first increment you set a TTL equal to the window size so Redis cleans up automatically. The entire check and increment is effectively atomic because INCR is a single Redis command. Simple, fast, cheap, but the boundary burst problem is real and you must acknowledge it whenever you propose this. Sliding window log solves the boundary burst completely. For every caller you maintain a sorted set of request timestamps. On arrival you drop all entries older than the window duration, count what remains and reject if you are at the limit. This gives you mathematically exact enforcement, no scene, no burst. The cost is memory. A caller making thousands of requests per second generates thousands of stored timestamps, and that scales badly at high cardinality. Sliding window counter is the pragmatic hybrid used by Cloudflare and Twitter in production. You keep exactly two counters, the previous window and the current window, and compute an estimated count by weighting the previous window counter by how much of it still overlaps the current sliding window. Memory stays constant at 2 integers per caller regardless of traffic volume. The approximation error is statistically negligible in practice, which is why this is the go-to choice for high-scale systems. Token bucket is the algorithm you reach for when you need to permit legitimate bursting. The bucket refills continuously at a configured rate, and each request removes one token. If the bucket is empty, the request is rejected. Because tokens accumulate when traffic is quiet, a caller who has been idle can legitimately send a burst up to the bucket capacity. This models real-world traffic patterns far more faithfully than a hard window, and it is why token bucket is the default in most API gateway implementations. The core refill logic computes how many tokens have accumulated since the last request by multiplying elapsed seconds by the refill rate. Tokens are capped at the bucket capacity, then one token is consumed for the incoming request. The entire state is two values, the current token count and the last refill timestamp. This is trivially storable in Redis as a hash, and the refill computation happens lazily on each request rather than on a background timer. Leaky bucket inverts the mental model. Instead of counting tokens a caller can spend, you model a queue that drains at a fixed rate. Requests join the queue. If the queue is full, they are rejected. The output side is perfectly smooth. Downstream services see a metered, constant call rate regardless of how spiky the input is. This is the right algorithm when your constraint is not the caller but the system you are calling, for example a third-party billing API that is contractually limited to 10 calls per second. Mapping the 5 algorithms against their key trade-offs clarifies the selection decision. Fixed window and sliding window counter are both constant memory options. The counter variant eliminates the boundary burst problem at negligible approximation cost. Sliding window log is exact but memory hungry. Token bucket and leaky bucket are complementary. Token bucket absorbs bursts on the input side while leaky bucket smooths output for downstream protection. Pick your algorithm based on whether your constraint is the caller's behavior or the downstream system's capacity. 3 algorithms dominate real-world rate limiter design. Each makes a different trade-off between simplicity, burst tolerance, and strictness. Understanding the mechanics and the failure modes of each is what separates a correct implementation from one that breaks under adversarial load. A bucket has a fixed capacity B, tokens drip in at a constant refill rate R tokens per second. Every accepted request consumes 1 token. When the bucket is empty, the request is rejected. The formal invariant is tokens at time t equals the minimum of capacity and tokens at the previous checkpoint plus r multiplied by elapsed time. You cap at capacity because you cannot store more tokens than the bucket holds. Token bucket gives you 2 guarantees simultaneously. Over any long window, the throughput cannot exceed r because that is the refill rate. But a client that has been idle accumulates tokens up to capacity B and can spend all of them at once, no delay, no queuing. That burst tolerance is exactly why token bucket dominates production API gateways. Real client traffic is inherently bursty, and penalizing it artificially hurts user experience without improving protection. This is the essential kernel of a token bucket implementation. On every request you fetch the stored state, compute how many tokens have accumulated since the last check using elapsed time and the refill rate, cap at capacity, then either reject if the bucket is empty or subtract 1 token and allow. The entire decision is O1 and requires only 2 fields of state per client, current token count and last refill timestamp. Leaky bucket is the most misunderstood algorithm in this space, so the distinction must be explicit. The meter interpretation produces perfectly smooth output, no burst ever gets through, overflow is simply dropped. The queue interpretation absorbs bursts by delaying them, but that requires storing a live queue per client, which is prohibitively expensive at millions of concurrent clients. In practice, if a library claims leaky bucket semantics, read the source, it is almost certainly token bucket. The difference that matters for design discussions, token bucket permits bursts, true leaky bucket does not. Fixed window divides time into discrete buckets, increments a counter per client per bucket, and resets at each boundary. The vulnerability is the boundary burst. A client sends the full limit of requests in the final moment of one window, then sends the full limit again in the first moment of the next. Both windows show a compliant counter, but the actual throughput in that brief span is double the intended limit. Window boundaries are usually predictable, top of the minute, top of the hour, so this is trivially exploitable, not a theoretical edge case. Fixed window earns its place for internal service quotas, course daily limits, or any scenario where an occasional boundary burst is an acceptable cost for operational simplicity. But for public APIs, billing critical limits, or any environment with adversarial clients, the boundary burst is a real exploit. The natural fix, sliding window counters or sliding window logs, trades some additional memory and computation to eliminate the boundary discontinuity entirely, which is the next algorithm we will examine. We now cover the two remaining algorithms, sliding window log and sliding window counter, before comparing all five side by side. Then we go under the hood on token bucket and sliding window counter to understand exactly how they execute in production code. Sliding window log stores every request timestamp in a sorted log per client. On each new request, you evict all timestamps outside the current window, count what remains, and either reject or append and allow. The window slides continuously with every single request. There are no boundary bursts and no approximations, just perfect accuracy. The precision comes with a real price. Every active client keeps every timestamp in the current window alive in memory. At generous limits and large user bases that balloons quickly, 100 million timestamps is not an exaggeration. Use sliding window log when fairness and exact accuracy are non-negotiable and per key traffic volumes are manageable. Sliding window counter keeps two fixed window counters, one for the current window and one for the previous. The approximate rolling count weights the previous window's counter by the fraction of the current window that has not yet elapsed. If you are 40% through the current window, the previous window contributes 60% of its count to the estimate. This is the algorithm Cloudflare documented using at billions of keys scale. The uniform distribution assumption is not perfectly true, but for typical traffic patterns the approximation error is small and bounded. The payoff is dramatic, regardless of traffic volume. Each key costs exactly 2 counters, constant memory, making this the go-to choice for high-scale systems. Mapped across accuracy, memory, burst handling, and best fit use case, the 5 algorithms form a clear spectrum. Token bucket and sliding window counter both achieve 1. Memory with good burst handling, which is why they dominate production distributed systems. Fixed window is simple but dangerous at boundaries. Sliding window log is the accuracy champion but carries a memory penalty that limits its scale. Knowing the algorithm names and their trade-offs is table stakes. What separates a production engineer from someone who skimmed a blog post is understanding exactly what state is stored, how it is updated, and why the implementation choices matter at distributed scale. We focus on token bucket first. Never run a background thread to drip tokens. That does not scale and wastes CPU. Instead, compute token accumulation lazily on every request arrival. You multiply elapsed time by the refill rate, cap at capacity, then check and deduct. All the logic fires exactly when needed and never when it is not. The entire runtime state of a token bucket reduces to 2 numbers. That is the insight that makes it practical in a distributed store. 2 numbers fit in a Redis hash, can be read and written in a single atomic operation, and cost almost nothing to serialize. 1 production gotcha. At very high refill rates, rounding timestamps to integer milliseconds can introduce token-rent errors. Prefer higher resolution time or scale your units accordingly. We now move into the implementation details that separate a toy rate limiter from a production grade one. 3 topics demand close attention: the exact Redis command sequence for the sliding window log, the weighted math inside the sliding window counter, and the concurrency failures that emerged the moment you go distributed. The sliding window log maps directly onto a Redis sorted set. The score is the request timestamp, and we use the timestamp as both score and member. In production, you would substitute a UUID as the member to avoid collisions when two requests arrive at the exact same millisecond. The logic itself is clean and readable, but it hides a critical flaw. Between counting and writing, another node can observe the same count, pass the same check, and insert its own entry. You intended to enforce a limit of n, but two requests squeaked through simultaneously. This is not a theoretical edge case. Under any meaningful load, with multiple application nodes sharing one Redis instance, it will happen. Wrapping the entire sequence in a Lua script makes it execute atomically on the Redis server, eliminating the raise window entirely. The weight calculation is the algorithm score insight. If the window is 60 seconds and you are 30 seconds in, the elapsed fraction is 0.5, so weight equals 0.5. That means half of the previous window's requests are estimated to fall inside your current rolling window. Notice the expire is set to 2 times the window size, not 1. When the current window later becomes the previous window, it must still be alive for the next window's requests to reference it. Set it to 1 window size, and you introduce a subtle undercount bug during window transitions. With no shared state, each node maintains its own counter. Set a limit of 100 requests per second and 10 nodes, and your effective global limit silently becomes 1000. Round-robin routing makes it worse. Each node sees only a fraction of total traffic, so every counter stays low and every request is admitted. The rate limiter becomes completely ineffective. Centralizing counter state in Redis is what restores a single global truth. Each option trades simplicity for correctness. Per node limiting is perfectly valid when you are protecting per node CPU rather than enforcing a global business quota. Sticky routing eliminates coordination overhead but shatters during rolling deployments and node restarts. Central Redis gives you one authoritative counter at the cost of a network round trip. And Lua scripts on Redis give you atomicity on top of that, which as we established is non-negotiable for correctness under concurrent load. The recurring theme across both algorithms is that the math is the easy part. The hard part is ensuring that read, check, and write happen as a single indivisible unit regardless of how many nodes are running concurrently. Get the consistency model wrong, and the algorithm is irrelevant. You will either overadmit requests or undercount traffic. Nail atomicity first, then tune for performance. Let's recap the key takeaways from this masterclass. If this helped you, hit the like button, subscribe for a new deep dive masterclass every week, and forward this to a teammate who would find it useful. Drop your questions in the comments. I read every one. See you in the next one.